Good afternoon, and welcome to NASA's Kennedy Space Center in Florida. I'm Sean Potter from NASA's Office of Communications, and we're here today to talk to you as part of the GOES-R mission science briefing. GOES-R is NOAA's next-generation geostationary weather satellite and is scheduled to launch this Saturday. Once it becomes operational, it will revolutionize weather forecasting for years to come. Now, we've assembled a panel here of experts to talk to you about various aspects of the mission, and I'm going to introduce them now. Directly to my left is Stephen Goodman, GOES-R program scientist at NOAA, the National Oceanic and Atmospheric Administration. Directly to his left is Joe Pica. He is the director of the National Weather Service Office of Observations. Next to Joe is Sandra Kaufman, deputy director of NASA's Earth Science Division. And finally, Damon Penn, assistant administrator for response at the Federal Emergency Management Agency, FEMA. Now, thank you all for being here, and before we take questions from the audience, each of our panelists have a few opening remarks that they'd like to make. So we'll start with you, Stephen.
All right, thank you very much. So I wanted you to know it's a big team that's put this all together. We have over 100 scientists across the country who've been working on the program for 1 or 2 decades now, developing the science products and the algorithms or the recipes for how to turn the measurements from the satellite into useful products for warning and forecasting. And you've heard earlier that GOES-R will make a tremendous difference, but I think we even underestimate what the capabilities will be. We only have about 30 new products that we make with the satellite, and we know there'll be hundreds more as we learn how to use the satellite. The main purpose of these products is to provide continuity from today's satellites into the future, but because of the advanced capabilities with 5 times as many spectral channels that lets us see different properties of the Earth and atmosphere, as well as the rapid refresh that we're able to do, which is 5 times faster than the current satellite, and then we have spatial resolution that's 4 times better, and so we see features now with GOES-R that we've never been able to see before. For example, we can see waves in the clouds, which are related to the turbulence that if you're flying on an airplane, you might encounter. And so we'll have early indication of areas to avoid, which we couldn't see before with our lower resolution. It was all smeared out. And I also put in a plug for space weather. Our new capability to image the sun will be 4 times that of our current SXI X-ray imager. And because the forecasters, when they try and diagnose the features on the sun that are going to lead to navigation problems and geomagnetic effects and communication outages, they take all the information they see, and it takes them minute to minutes to assemble that information. Well, now they have what they call a thematic map they can put together where they take all the information, and within seconds now they can see how things are revolving. So we can do it for the Earth-based high-impact weather, volcanic eruptions, to typhoons and hurricanes and severe storms. And right now we have a major fire outbreak in the southeast, and we'll be able to see the aerosols and the characteristics of the smoke and dust in that fire, as well as Matthew, which someone mentioned earlier, and I'll comment on that later. Thank you.
Great, thank you, Stephen. I will turn it over to Joe.
Thank you, Sean. It's an honor to be here for this momentous occasion. At NOAA's National Weather Service, we're very excited about the launch of NOAA's GOES-R satellite. And most importantly, we're ready to use the information when it's available. We specifically want to recognize the NOAA GOES-R program, specifically Greg the program manager, and Steve, my panelist to the left, for all their efforts over the past few years to ensure that there was collaboration and support for activities to make sure that we're ready to use all these revolutionary products. So thank you, Steve.
Thank you.
It's our mission at the National Weather Service to provide weather and water forecasts, warning, and watches for the protection of life and property. To do our job, we rely on a whole host of observations, a whole portfolio, a key one being geostationary satellites, not only to monitor and provide information about evolving weather systems, but also to feed into our weather models to help forecast weather for tomorrow, this weekend, next week. We're excited about GOES-R because it's going to help us to do our jobs better. You've heard the terms game changer, revolutionary. It really is. It's going to be like looking at, instead of black and white TV, HD. NOAA's GOES-R will scan the skies 5 times faster than the current GOES system, with 4 times the spatial resolution and with 3 times the spectral bands. This means we'll have better quality data at high resolution far more often than we do today. Forecasters will have far more detailed views of weather systems. We'll be able to see rapidly developing events in real time. And when we see an evolving weather system, we'll be able to zoom in and use that high spatial resolution to take pictures in 16 different spectral channels every 30 seconds. This spectral imagery, combined with our Doppler radar data, for example, will improve our understanding of whether a storm is growing or decaying. It'll help us track severe storms, including tornadoes, forecast wildfire movement, track plumes from volcanic eruptions, and tell whether a hurricane is intensifying. This past year, we've seen a number of destructive heavy rainfall and flooding events. With better quality data from GOES-R, our forecasters will be able to better see where those rain bands are actually impacting us, giving them more confidence in predicting where the flash flooding will occur. Getting this out to the public in a more timely manner, and even to our partners in FEMA so they can manage the response. Our aviation weather forecasting ability will also be improved. More accurate and detailed information on the occurrence of fog and ice, wind, and lightning from GOES-R will help with aircraft flight routing, making sure that all of our family members are especially traveling well during the holiday season that comes up, like we're doing today with our current GOES network. So I mentioned the Lightning Mapper. We're very excited about this new capability in space because it helps forecasters identify storms that are the biggest threat. That basically, lightning is correlated to some of the most severe weather. So we can see where hazardous conditions such as damaging winds, tornadoes, large hail, and flash flooding will occur. GOES-R will also improve forecasts for space weather. Space weather instruments will monitor the sun and the environment in space, so we can provide watches and warnings that have to do with radio communication outages, navigation, and power grid impacts. NOAA's GOES-R is a major step forward in our effort to build a weather-ready nation. By advancing our observation capabilities to the next level, we will be able to offer new and improved forecasts, products, and services to help save lives and property. It's an honor to be here for this event. Thank you.
Great, thank you, Joe. Sandra, you're up next.
Thank you so much, Sean. To me, it's a really, truly pleasure to be here today. Part of my career has touched GOES in many ways, and in a past big nation, I was the Deputy Systems Program Director for GOES-R. So to see this mission finally launch is truly a treat for me. So NOAA and NASA has had a long collaboration developing and launching the geostationary meteorological satellites that dates back more than 40 years, as we have heard many times before. With GOES-1, that was launched on October 16, 1975. With this latest geostationary satellite, this is a quantum leap in science and technology, and it will truly revolutionize weather forecasting. Once operational, GOES-R will become GOES-16. NOAA GOES-R will provide 3 times more spectral bands. The current GOES has 5. The new GOES is going to have 16 bands. It's going to have 4 times better spatial resolution, and it will be 5 times faster, which means more frequent and detailed information for forecasters to consider in support to the public and the aviation community. That means the GOES-R will be able to image everything in the hemisphere in the same length of time it takes the current GOES series to provide one small image of one little stormy region. So increased imagery over the short time period will provide more timely and informative data to forecasters everywhere in the Western Hemisphere. GOES East and GOES West right now do not have the capability to take those full images every 5 minutes. The current GOES satellites scan the full hemisphere every 30 minutes, or the United States every 15 minutes, or a stormy region every 5 minutes, but not all at the same time. This change in imaging is a mission requirement for GOES-R that will enable simultaneous rapid regional coverage and continuous hemispheric weather monitoring. As a result, we can expect noticeable improvements in the quality, detail, and speed of forecasts, including the prediction of severe weather events, tropical storms, and hurricanes that pose danger. GOSAR will feature 6 brand new instruments: ABI, EXIS, SAIS, GLM, SUVI, and the magnetometer. Briefly, I want to highlight the GOSAR Lightning Mapper. This instrument will be the first operational space-based detection system for total lightning activity over land and water. The basis for the GLM is the lightning imaging sensor that flew on the NASA JAXA TRIM mission from November 1997 through April 2015, providing first-ever tropical lightning climatologies. We are very excited about the GLM because it will tell us more about lightning activity than we have ever known, which will improve forecast and decision-making. Trends in total lightning that will be available with the GLM have the promise of providing critical information to forecasters, which will allow them to focus on developing severe storms much earlier than they can currently, and before these storms produce damaging winds, hail, or even tornadoes. NOAA's GOSAR will be a game changer for weather forecasts for our nation and throughout Latin America and the Caribbean. Each day, weather forecasters throughout Latin America use data from NOAA's geostationary satellites in similar ways as their U.S. counterparts. The key difference is that data from radars, soundings, and aircraft, which are incorporated into NOAA's forecast models, are sparse throughout Latin America. That's why NOAA's geostationary satellites and the upcoming advanced GOSAR satellite are so crucial in protecting lives and property throughout Latin America and the Caribbean. We are looking forward to working with our colleagues there to help bring about forecast improvements into the future. The GOSAR satellite will significantly improve the detection and observation of environmental phenomena that directly affects public safety, protection, and property, and our nation's economic health and property, and that of Latin American and the Caribbean. I'm going to repeat this last sentence in Spanish for our Latin American friends. El satélite geoestacionario GOES mejorará significativamente la detección y observación de fenómenos ambientales que afectan directamente la seguridad pública, la protección de la propiedad y la salud económica y prosperidad de nuestra nación, América Latina y el Caribe. Back to English. NOAA and NASA's collaboration goes beyond the meteorological satellites. NASA's Earth Science Division provides new real-time data and information products from our NASA's research satellites, which are used routinely by NOAA and other operational agencies. We support NOAA's operational capability by supplying data products ranging from atmospheric dynamics, atmospheric composition, sea surface wind speed and direction, wave conditions, aerosol data, and many other products that are fed into the numerical models to help the weather forecasters. In addition, together, NOAA and NASA develop and are operating SUMI MPP, a complementary LEO mission that both advances research and serves the operational NOAA community. We are very, very proud of our partnership with NOAA, and we are looking forward to many more years of collaboration. Thank you, Sean. Back to you.
Thank you, Sandra. And finally, we'll hear from Damon Penn from FEMA.
Thank you, Sean. Thanks for having us today. I don't think it'll come as any surprise when I tell you that weather forecasting is critical to decisions that emergency managers make, not just at FEMA, but at the state and local level. And our days all begin and end with the weather forecast. And not just the traditional forecast where during hurricane season we'll talk about what the cone of uncertainty looks like, and not just during tornado season when we'll talk about what kind of conditions are favorable for tornado formation. But wildland fires, as we mentioned in the southeast, flood inundation mapping and prediction and surge products, all of those things together all turn into decisions that emergency managers have to make. And the importance of having accurate forecast is because the accuracy turns into time for us. And one thing you can't get back during a response to an emergency is time. And once you get behind, you never catch up. And there are decisions that have to be made several days in advance. For instance, if you're talking about evacuating a major metropolitan area, you may have to make that decision 4 days out just to be able to get everything going and get people out of the area. If you're talking about moving in supplies and commodities, that takes several days. If you're talking about solar weather events, that may take several seconds or several minutes. So accuracy turns into time, and time can be important from minutes for us to hours, to days. But all are important and all really impact on decisions that we make. Because really, once you make a disaster decision, it's made. Once you decide to evacuate, you can't unevacuate. Once you decide to put commodities on the ground and you put them on the ground in the path of the storm, you can't pick them back up. So our relationship with NOAA and the kinds of products that NOAA provides us are critical to what it is that we do. And the more accuracy and the more information that we can get, then the better we can serve the public and the better we can help manage disasters and take care of our survivors on the ground. So thank you.
Great. Thank you, Damon, and thank you once again to all of our panelists. Now, we're going to take your questions in just a moment, but before we do, we're going to go back to Stephen Goodman, who has a video to show us demonstrating some of the capabilities of GOES-R.
Right. So I've always told people that the imagery will speak for itself, and I don't need to narrate it, so let me give that a try. What you're looking at is a developing outbreak of severe storms. This is taken with the spare satellite that was mentioned earlier today, and what you see there, that line of clouds moving south, is called an outflow boundary, and you can see the differential motion of the clouds. Over on the right-hand side, you see clouds at low levels coming into the storm, and you see the storms developing as that line comes through. So when that outflow boundary hits these developing cumulus clouds to the south, it develops into another major storm system. And it's the animation is so quick, I guess it's hard to pick up on this video. So I did narrate it a bit, but this is with the spare satellite. So what you just saw would have been the rapid scan capability of GOES-R, but at low resolution, because the current satellites on orbit only have 1/4 the spatial resolution. So a lot of the detail we can see at cloud top and with the convergence to clouds will help the forecaster, especially if there's a severe storm outbreak. It can help them to determine if they need to extend their watch area beyond the current time, because they can see the new development that's happening. Thank you.
Great. Thank you. Thank you, Steve. Some exciting changes coming with GOES-R. Now we're ready to take your questions, and we have several reporters here in the audience with us. We'll take questions from them, as well as questions from folks calling in on the phone. And if you're joining us via social media, you can ask a question using the hashtag AskGoes, and we'll get to those in just a few minutes. But we'll start with a question here in the room, and we've got one right here in the front row. Could you please identify yourself?
Sure. Ken Kramer, Universe Today and the Northeast Astronomy Forum. My question is specifically about the lightning mapper, this first lightning mapper. Can you talk a little bit more in detail? How will you use this lightning data to warn about severe weather? How will you use it to warn about tornadoes and get that data, because the latency period is critical, to get that data to FEMA so they can issue tornado warnings? How will that all work?
Let me start on that one, since I started with that instrument in 1979. We worked on it a very long time when we started development at NASA, and then it became the new instrument for GOES-R. So the idea behind the instrument is that when you have rapidly developing storms, it can give us an indirect indication of the strength of the storm updraft. And the storm updraft does all the work. And we don't have any instrument, even the radars, that directly tell us how the updrafts are intensifying. We can see the precipitation cores as they ascend. And what happens is you take the raindrops and lift them up higher in the cloud, they freeze and they form ice. And it's the collision of ice particles in a rich region of liquid water or water vapor that enhances the electrification process. So the stronger the updraft, the more collision of particles and the faster the rate of electrification, and then that's released by the lightning. And so we connect the lightning to the rapid development and intensity of the storm updraft. And if you have a rotating thunderstorm, say an incipient tornado, they take wind shear from the environment. And taking that wind shear then and the updraft turns that rotation, we call it vorticity, up into the upper parts of the cloud. You're connecting both what's happening aloft in the cloud and what's happening down below. And that's where the lightning is giving us this additional lead time, because we see these surges we call lightning jump, and we're able to relate that then to the intensifying storm. So imagine a sea of storms out there. You're a forecaster. You got 20 storms that you're focused on. And when you see one of these storms with a rapid increase in the lightning, you see the radar echo, as Joe was saying, intensify, and then we're looking down with the imager and we're seeing cloud tops growing. You connect all that together and it really helps the forecaster, what we call the situational awareness. And so from that, they're able to discern that, yeah, I need to pay more attention to that storm or that storm. And then they have the diagnostic information that's going to help them get a warning out earlier.
Did anyone else want
Joe?
to add on to that?
So I would just add a small piece is that it's a complementary observing network, and it basically will give us advance notice to where do we focus looking at the radars? Where do we focus so that we can provide that additional time? And the lightning was one of those early contributors. I think we're going to learn a lot because it'll be the first one we have in orbit. So I don't think we know everything how we're going to use it yet as well.
Great, thank you. Okay, we got a question over here.
Dan Satterfield, WBOC in Salisbury. Steve, you and I have been down to the new GOES-R dishes. GOES-R is downlinked at Wallops Island, which is my viewing area. So two-part question. One, are the dishes now ready to go? And two, how long after launch will the data be acquired at Wallops Island and start coming down there?
Okay, well, I'll take a shot at it. It might have been a better question for the earlier panel, but my understanding is that they are ready to go. And our game plan is that once we launch the satellite, we have to do outgassing after we reach orbit, about 15 days to reach orbit, 30 days to get all the contaminants away from the satellite instruments. And then we turn it on, and then we'll start providing data to our calibration validation teams. And we'll continue doing that for about 6 months. And then NASA will hand over the satellite to NOAA. And then we'll continue another 6 months of validation. When we reach the validation point on the products that we determine they're fit for use by the forecasters, we'll turn on the GOES rebroadcast system, which is the downlink. And then the forecasters will have the data, and they know that we're still tweaking things and trying to get it all optimized. And so they'll take things with a grain of salt, but then by the end of a year on orbit, then we'll have validated our products and they'll be ready for everybody to use.
Great, thank you. Let's see, do we have any more questions here in the audience? Second row here by the aisle.
Hi, I'm Kelly Cologno with Northwestern University Medill, and I was wondering if you could tell us a little bit about how the satellite can or will be used in climate change research or studying climate change.
I'll make a couple comments in there. So one thing the satellite has that we haven't had before is has an on-orbit solar calibrator for the instrument, for the imagery. We've not had that. The low Earth orbiting NASA research satellites have such a capability, and we basically have now replicated that for geostationary orbit. So one, the data will in fact be more accurate. People have always said the weather data doesn't need to be as accurate as climate data, but the new data from GOES-R will actually be more accurate than we've had before. One of the things that GOES-R contributes is unraveling the diurnal cycle. What I mean by the diurnal cycle is we have generally the global observations are in low Earth orbit, and so you get a snapshot every maybe 12 hours, if you're lucky, maybe every 4 hours if you've got a constellation with many satellites, and yet it's still difficult to determine. Say we're trying to diagnose cloud properties, and we know how do cloud properties change over decades, or how do they change even interannually? Say we have an El Nino event or an El La Nina event, and we actually are going to have a La Nina event most likely this coming winter going into February. And so what the satellite would tell us is, what are we missing when we're trying to characterize the clouds by having sampling throughout the day? That's what I mean by the diurnal cycle. Instead of coming over at 1 o'clock every afternoon, the clouds aren't the same at 1 o'clock in the afternoon. Sometimes they're still developing, they're not mature. So it'll help us with that. The other way I would say is extreme weather. So right now, we don't know what the variation of extreme weather is, but we know from, as Sandra mentioned, we had a lightning mapper in low Earth orbit on the NASA Tropical Rainfall Measuring Mission for 17 years, and now we're going to have 20 years more extending that climate data set. So once you have 30 years, generally people say, I got a climate data set, and we can look for those variations. So I think GOES-R and the rest of the geostationary satellites that Europe is launching, Japan, you heard, has launched, China will launch, and so we're going to have a global constellation of geostationary satellites that have nominally the same capability as GOES-R. And so I think it'll contribute both in how do storms and clouds and the environment vary over the course of a day, and then also extreme storms, severe storms, how do they vary, say, over decades?
Great. Thank you. Over here in the second row.
I had a question about accessing the imagery afterwards. So even right now, with say 1 minute imagery, satellite imagery, for example, it can be difficult to find. For a TV meteorologist, we have access to our data service providers and the data that they and images they provide us. But for the general public who are more savvy about just going to the web and looking for the data, will there be a way to get at this really cool, 30-second high spatial resolution satellite imagery?
I'm sorry, and could you just identify yourself, please?
Oh yes,
Name
I'm
and
sorry,
affiliation.
Jen Carfagna from the Weather Channel.
So if I can start on that one. So we have a satellite analysis branch in NESDIS, in the satellite service, and they have a web page, and they're going to update their web page that we currently have to show the native temporal resolution of the data. So when we take 1 minute imagery or 30-second imagery with the imager, and we have the 20-second latency from the Lightning Mapper, they will have web pages that anyone will be able to access to see that. And also I should mention, we've been working with the broadcast meteorology providers and showing them the value of the data and say, don't let this rapid scan information drop on the floor. I don't know if I can mention who the providers are, but one of them was at a conference with me, and he pulled out his cell phone and he says, here's the Japanese rapid scan imagery. Isn't this amazing? And I said, you bet it's amazing. So they're attuned to that, and I've been talking with Dan here for years too, and he's helped advocate that they need to update their delivery system so that you, the users in the broadcast industry, can take full advantage of what GOES-R can offer. And I should say, we've been doing a demonstration at NOAA's Hazardous Weather Testbed to get some of the broadcasters attuned to what we might be able to offer. And one of the reasons we did that was because Joe and the Weather Service are putting out the weather information to the viewer and the TV stations. It's really that last mile that's going to have the big impact for the public. And this loop that I showed you, if we can show that kind of loop on the air, I think the viewer can personalize that the risk is real and the storm is coming at them, and they'll maybe be more likely to take action. And that's what we need, is people to take action to be safe.
Great. Next question. In the back row on the side.
Hi, Mike Augustinek with CBS in Minneapolis. I'm sorry if I missed you already answering this question. We know the new temporal resolution of the Lightning Mapper. What's the spatial resolution?
The spatial resolution for the visible channel is 500 meters, third of a mile or so. It's 4 times better. And then for GLM, it's 8 kilometers spatial resolution. And there's an interesting innovation in the design of the detector that allows us to keep that spatial resolution across the oceans. And so had we not done that, we would have had spatial resolution, say, of 30 kilometers, which is larger than an individual storm, and that's what we would present to aviation industry and the FAA. But because we're able to pull in the resolution as the instrument is looking further out from directly beneath it, we'll be able to have storm scale spatial resolution pretty much all the way across the field of view. And the field of view for GLM from both satellites combined will be from the west coast of Africa up to Edmonton, Canada. It's about 54 degrees latitude. Same down to the South American in Chile, and then all the way over to the east coast of New Zealand. And so while the imager gives us a larger field of view, the GLM will cover most of that airspace. And we know from talking to Joe's director at the Aviation Weather Center that they're very excited because they don't have radar over the ocean. The aircraft radars are small and they don't see over the horizon, and now you can take the imager and the Lightning Mapper, combine it together, and effectively provide radar-like information out over the oceans where the hazardous storms would be.
Joe, do you have anything you want to add to that?
No, I think Steve covered that very well.
Great. Okay, our next caller is, we've got a question on the phone from Mark Gotch. Go ahead, Mark.
Yes, good afternoon. Thank you for this very informative science briefing this afternoon. Mark Gotch, Historical Aerospace News. Please, can you explain how the advanced baseline imager technology was developed and how will it be used going forward? And also, one other question, how will solar flares be seen differently and what will this mean to the future of forecasting? Thank you.
Thank you. Who wants to tackle that one?
Well, I'm not sure I could remember all the pieces. If I start at the beginning, Harris Corporation has developed the imagers that we've been flying on our satellites for the current series, the previous series, and back in around 2004, we did some feasibility studies with a number of vendors on the different possible architectures for the different instruments. And so we settled on the Harris design, which was able to give us 16 spectral bands. Initially, we were hoping to get even more spectral bands, but it's expensive and challenging. So we settled on 16 spectral bands, and the scientists had done studies as to what each individual spectral band might offer. For example, we have a spectral band at 1.39 microns, which allows us to see cirrus clouds, and so that was something we weren't able to see before. We have 3 water vapor bands, and so for you who watch the water vapor image on TV, that's the upper level water vapor, but now we can see deeper into the atmosphere, and that'll let us see when the atmosphere, where the atmosphere is destabilizing more. And I should mention, let me use that as a segue into tropical storms. So from the Himawari Japanese satellite, which is also purchased from Harris, the same instrument technology, the only difference really is that we're operating the satellite, taking 1 minute images, and they take them 2.5 minutes apart. But we have some data from a typhoon called Sodalor that hit Taiwan, and I asked our scientists who work with the wind, we call them atmospheric motion vectors. You can use the cloud and water vapor as wind tracers. So anyway, they took that and these water vapor channels. I said, so I know that we can see things, but what's the real impact? Is there impact on the model? So they did a process we call data assimilation, and they bring these data into a best analysis. And to my surprise, even when they did the forecast track for this typhoon, they actually reduced the forecast track error. Where I expected improvement was in the intensity. And the intensity in that case was indeterminate. So we've only done a couple of cases, and you have to give us time to collect enough samples with the actual GOES-R satellite to know what the true impact is. And if you just give me another second, let me comment on Matthew. So I figured someone would ask about Matthew, right? And so I talked to the National Hurricane Center, the folks we work with very closely, and I said, what would have been the possible impact of having GOES-R on orbit? And it turns out that where the forecast models and the forecasters missed it was down in the Caribbean when they were expecting the storm to not intensify so quickly. And it turns out that all the information that GOES-R provides, for example, we mentioned the lightning mapper. They've been doing some work looking at how the lightning's related to rapid intensification of tropical storms and hurricanes. And it turns out that from ground-based networks that we have today, they didn't see the lightning signatures that would have told them that they would have had the strong shear. So that's the key thing. Hurricanes don't like shear, it tears them apart. And so they didn't see that signal. So I think GOES-R, because we're able to map the motions of the clouds and also to be able to map the lightning, I think both will contribute to picking up signals like that you might be missing. So that's what they say, the Hurricane Center forecasters, is a potential benefit we would have had we had GOES-R. Maybe, Joe, you have something to add on that.
I would just add, that we are very excited and we are preparing to use those atmospheric motion vectors, those derived motion winds from the imager. So we're very excited about what the possibility is for how that can improve our regional modeling. Another way we're trying to use the spectral analysis, Steve gave some examples of that, but if you're looking at fires in the southeast, we're going to be able to look at it very closely and even see, based on the spectral bands, what's burning, what is it doing, which way is it going, and so that can really inform some of the efforts that's being provided for fighting those fires. So those are, some of the new ways we'll be able to use the capabilities on GOES-R.
I just wanted to go back to the original question on how the technology came about, and it was really way early, around 2000s, and we issued completed formulation contracts working with various companies to develop, mature the approaches that we ultimately chose in 2004 to develop the ABI instrument. And as Steve pointed out, you know, we have a long history working with Harris, developing the GOES-I through M imager and sounder, which also flew on NOP. And ultimately, Harris was also picked to develop the ABI for the GOES-I.
I know the question also asked about imaging the sun.
Right.
But before I answer that, let me make one comment I don't forget about the numerical weather prediction forecast models. Where we're seeing the impact with these motion vectors, it's largely attributable to the higher spatial resolution. So when we calculate how the clouds are moving and the water vapor is moving and we get a wind vector from that, that depends on how well we did the clouds. And it turns out because we have 4 times the spatial resolution to get the clouds, we can more accurately assign the height of that motion vector. So if we have the right vector of the wind, but we put it at the wrong altitude, that's going to mess up the models. So the more accurate we can do that, and we've actually determined from our GOES-R algorithm, our recipe that we're using, that we can reduce the speed bias by 1 meter per second based on experiments with the Himawari, which is a huge benefit to the global models. So the question earlier about how the mid-latitude's going to benefit from GOES-R, it's the fact that we're able to put these motion vectors into the numerical models, and that's going to have the biggest impact, say, on the extratropics by making those model forecasts more accurate. On the sun, so I don't forget SUVI and the sun I mentioned earlier, so we'll have 4 times the spatial resolution. You'll have crisp imagery to better see, for example, solar flares. If we have a solar flare, we'll be able to determine more accurately its extent, so where its source is and where it's extended to. And we're also going to be able to diagnose that more rapidly because we have the higher resolution. And actually, SUVI is a bit faster than the current satellite as well. So everything's faster, everything's got more resolution, and it's going to be amazing.
Great. Thank you very much. We have, I believe, one question on social media. So John Yembrick from our social media team, please tell us that question.
Thanks, Sean. This question is, once in orbit, what potential hazards or fail points are there where it maybe prohibit you from getting accurate data? Or are there any?
Well, I can speak mostly to the Lightning Mapper. It's got a charge coupled device detector, and so high energy particles can penetrate the spacecraft skin and they can get to the instrument. And so in that case, we could lose pixels if we had high energy that would impact detectors. So right now, the mission that Sandra mentioned that had been on orbit for 17 years, we never lost any pixels over that time. It's a solid state device. So something like that could happen and it degraded over time, then maybe we would lose a piece of our field of view if that were to happen. In the case of the SUVI instrument, it's got an ultraviolet filter. Ultraviolet filters are very touchy and very difficult to manufacture. In fact, I believe we're replacing the UV filters right before we launch. Maybe we've done that already. They don't like water. Water is an enemy of ultraviolet filters. So if something were to happen in contamination, then that could affect the full field of view that we would get from the instruments. And of course, hopefully there's be no issues with the telecommunication aspects of the satellite to get the data down to Earth to use it.
And more than that, with the launch, there is dangers. Deployment of appendages, there is danger, and we have to still achieve geostationary orbit. It's going to take 9 days to get there, so the thrusters have to be able to get us ultimately to where we want to go. So, that's why we test and test until, we know that things are going to work. Mm-hmm.
Okay, other questions here in the room? We've got one right here near the back.
So, Matt Safino, KGW TV. Back to the GLM. If I heard correctly, the technology of the Lightning technology on TRIM was based on 1997 technology. So is the new GLM instrument similar to that, or have we advanced beyond that, and how much?
The biggest advancement over what we had with the Lightning imaging sensor, it had 128 by 128 pixel array. Now we're talking 1360 by 1320, so we got a much bigger array that we're detecting near the full disk of the Earth. And the thing that's going to really change things is we had a transponder bandwidth for that mission of 8 kilobits per second. And what would happen is when we would fly over a very intense storm or over the South Atlantic anomaly, which is a high radiation area off of the South American East Coast, we would saturate the instrument, and so we couldn't take any data. So now on GOES-R, thanks to all the developers, we have 7.7 megabits per second. What does that mean? That's a huge difference. That means that we can lower our detection threshold and see more of the lightning, even the weaker lightning, than we could before. We're predicting a greater than 80% detection probability of all types of lightning, even if it goes to ground, because a ground strike has channels up into the cloud, and the light that's emitted makes its way to cloud top, and we see it. And so we have a number of filtering algorithms. We have 8 right now that take the raw data that's sent to the ground from GLM and remove things like glint that you get from the sun reflecting off the ocean surface. We also have radiation effects, as I mentioned earlier. And so actually, after all that filtering's done, we really see the lightning very well. That's a huge advantage over what we had with the original instrument. We still operate at the same wavelength in the near infrared because that's where we get about 10% of the total energy from lightning. So there's no reason to change that. So it's the bandwidth is really the big innovation since the earlier instrument.
Great. I think we have time for 1 or 2 more questions. The audience, do we have any more? If not, in the back we have one more. Okay.
Hi, Nick Stewart, KHQA, Quincy, Illinois. Question for FEMA. We talked obviously very well about how this is going to, predict disasters, how you might be able to prepare for that. How about post-disaster? How are you looking to use this technology to kind of look at recovery efforts?
Yeah, that's a great question because people tend to think that disasters end once response ends, and it really does not. Recovery goes on for several years. But immediately following a response, as you know, you have quite a vulnerable population. You've got people that have been displaced. You've got people that have damaged homes. You have limited transportability because you have debris in the roads. You have all those kinds of things. So having accurate weather forecasting then is as important as it is prior to the event, because that will determine how we can actually get commodities moved and distributed throughout, how we can actually evacuate the our vulnerable populations, how we can get people back into the areas that they came from, all of those things. So we pay as much attention post-event as we do pre-event. So again, the better forecast, the better decisions we can make, and more timely our decisions.
Great. Thank you, Damon. Thank you once again to all of our panelists. That's all the time we have today for this briefing, but I want to remind you that you can find out much more about the GOES-R mission by going to the website that you'll see on your screen. And you can also follow us online and on social media in the days leading up to launch this Saturday. And be sure to tune back for more NASA TV activities then. Thank you for joining us.